Hey guys, what's up? Eddie Aho here with KissAnalog.com. Guys, today I want to talk about some really important specs on oscilloscopes. So you know how to kind of see through the BS or at least kind of have a better understanding of what the specs are and how to choose a scope. And you know, when you're watching these reviews, you can go, okay, that's important. Okay, let's see how these three things work together to see how well the scope works versus focusing on this one measurement or this one spec. Okay, and so that's what I want to do. I'm here with Pico. This is a new 3000 series. I wanted to do a review on this so bad, but I thought, you know what? I need to talk about the importance of specs and what they really do, and so you understand it, okay? And maybe you already do. Maybe you understand it better than I do. And leave your comments down below. Some of you guys are really good at filling in, like educating us, so please do that. Now, this Uni-T back here, very impressive scope. This Pico 3000 series, another very impressive scope. But these scopes are expensive. You know, they're not, you could find really super awesome scopes, just amazing scopes for under $1,000, you know, easy, under $500 even, you know. Uni-T has an awesome scope right around $500. It's just amazing. So, well, you know, why go to a bigger, better, more expensive scope? Now, here's the thing. I've been watching some reviews lately, and I saw this new scope that's out, and it has a whole bunch of gigasamples of, I mean, the sampling rate's just crazy high. It's like 5 gigasamples or something like that. Not to say these guys aren't, but I'm just saying that for the cost of this scope, it's much less expensive than these. So why would you buy one of these when you can get one of, you know, that new scope that hit the market that has crazy 5 gigasamples? Well, it's kind of like buying your car and somebody says, hey, this thing can go 0 to 60 in, you know, whatever, 5 seconds. And you're like, whoa. But then how well does that handle? You know, what if I am a racer and I do want to go fast, but what if I'm going in ovals or figure eights? How well does that handle? How well does the stick shift work? Is an automatic. Hopefully it's not an automatic if you're a race car driver, but you know, so there's a lot of other things about the race car. You know, even if it is a race car, there's a lot of other parts of that race car that are very important, right? So if somebody just got lots and lots of horsepower or somebody just made a car super fast, but they didn't focus on suspension, steering, all the other things that go along with driving a car, you're like, yeah, okay, you know, if I'm only going to do drag race, then great. It's drag race specific. But, you know, sometimes I want to race around a figure eight or an oval track, or, you know, there's other things you want to race. Maybe you're not a race car driver all the time. Maybe you just want to drive it every day. So there's a lot of other things to think about when you're buying a scope. And I wish when these reviewers just talked about like how amazing this scope was, I kept on waiting for them to turn a page and tell me, you know, what else it does and what else it does. But when they just, you know, focus on that one thing, I'm like, sounds like a one-trick pony. So, okay, guys, remember back when digital cameras first came out? If you're my age, you probably do. They had so many megapixels, and then the next year, the megapixels would like double or quadruple, and you're like, wow, I gotta, you know, this old D100 Nikon I need the D200, I need the D300, need the D400. And so it was just this race of megapixels. And I think it was Canon that in their next year, they went, instead of higher megapixels, they actually dropped them from the year before. And I think all the other competitors were like, dude, what are you doing? You're not playing the game fair. We're supposed to be racing for megapixels. And Canon is like, Well, we're more interested in the quality of the picture. And, you know, in the beginning, when you got more megapixels, you got better resolution in your pictures. But pretty soon it's like, can I tell the difference? Maybe if I have a 5 foot by 10 foot, picture on the wall, maybe I can see the, difference. I don't know if I could even then. And what Canon found out, I believe what it was, is when the pixels get so small, they're not as light sensitive. So they're not as good as low light situations. And there's a lot of low light pictures, and there's a lot of pictures where you have low light and high light. And so they found, hey, let's make the pixels bigger because they seem to work better that way. And so they kind of went the other way, and then they did other things to improve on the picture quality. And they got out of the megapixel race, and they started to talk about other features that were important. And then that made it more difficult for the marketing people, because now they're like, oh, geez, we can't just compare this one thing. Like, come on, now we have to do other things to our camera as well. Jeez. So I think Pico is like Canon. They do so many things so well. The one thing is their memory, their deep memory is crazy. So maybe they do have a fixation on memory. But I mean, there's all the other things they do so well as well. So yeah, it's just a killer scope. Now the Uni-T, same kind of thing. So these kind of scopes in this price range here, they brought all the parameters of the scope up. So they're like, okay, we beefed this one up, but we beefed up this parameter, beefed up this parameter. And for instance, the scope, you have a vertical section, right? That's an amplifier that amplifies the signal that you put into the BNC input, right? And then you have the horizontal, and the horizontal changes the, how it compresses your signal or stretches it out. It's a time base, right? Then you have a trigger section. The trigger section is very important as well. All the different ways you can trigger. Now, like these picoscopes, I think they take it to another level. But this Uni-T, these new scopes, they're all going to another level in triggering. And triggering is so important when you're trying to capture signals. You guys know that. So the zoom feature, the deep memory is huge. That's what makes, in my mind, that's what made digital scopes catch up to analog and surpass them. That's why we don't see analog scopes anymore. It's a big reason is the deep memory finally got big enough to take over. I mean, when I had my first Tektronix digital scope, I had a Tektronix analog scope too. I had two scopes. And when I wanted to save waveforms and do all the digital stuff, I would pull out that scope. But it wasn't good enough. I didn't trust it for capturing certain things because of it didn't have the deep memory, there was no deep memory. So lots of different things. Besides those, basic operations, there's all these other things, which I want to show you. The FFT, for instance, that's a newish thing that came out. When Tektronix in the lab, we'd have these little chips that we'd plug in the side of the Tektronix scope to give us advanced FFT. And today, the $500 scopes kick that FFT's butt. They're just awesome. But today's FFT, well, and actually Uni-T's $500 scope is pretty impressive on their FFT. So, and I've shown some scopes around, less than $1,000 that are really amazing FFTs. People don't use the FFT as much, I don't think, or as much as they will. I think people are just starting to learn, but the scope manufacturers have been improving on that. And like the FFT on this guy is just another level. So I want to show you these things, but I want to talk about the sampling rate and why it's like the megapixel thing with the cameras. Why it's getting to the point where it's meaningless. I mean, within a certain... Anyway, I just want to explain to you. It's not meaningless, but it is. There's a bunch of factors that come into play at the same time. And So why, when you buy a scope, does it come with a certain number of gigasamples? Okay, well, you know, what's the sampling rate? All right, guys, so that's what I want to explain. So I want to pull up my chart. You guys, okay? All right, so I want to pull up this simple graph. This is my scope thing, the voltage here, the time here, here's the sine wave, okay? That's one cycle, right? So when you have an analog signal like this and you want to digitize it, you want to sample that thing so that you can rebuild it. There's a Nyquist theorem, right? And it says you have to take 2 samples of this in a cycle. So if this was one cycle, you need to take 2 samples in that cycle to recreate this waveform. And it's actually a Nyquist dash Shannon theorem. People usually just leave off the Shannon, but maybe that's not fair to Shannon. I think he's the one that proved it, like in the late 1940s or something like that. Nyquist did a bunch of math, and Shannon proved that it worked. And, you know, 2 points. Well, then they actually say at least 2 points, or a little bit more than 2 points. And the reason why is if you sample, say, here, and then the next time it samples a couple more places, and pretty soon it can rebuild this waveform. So they use their math and all that, and they figure out, like, you know, how to rebuild this thing, okay? But what would happen if you sampled here and here, or here and there? That's 2 times in a cycle, but they're both 0, so it looked like 0 volts. So that's why you have to sample a little bit more. And there's a great paper that Keysight wrote that talks about all this stuff I'm going to tell you. I'll put a link down below so you can read that. It goes in depth, and they did a really great job. So anyway, what it turns out to be is most scope manufacturers, I think pretty much all of them, the ones I've done the math on, is they do 2.5 samples, okay? So that way you can never fall on the 0 more than one time. Maybe you fall on this one, the next one's going to be on this side of 0, and then over here somewhere. You know, you're going to get 2.5 samples, okay? So the 2.5 samples works. That way you never get just 0 volts. All right. All right. So mathematically, how does that work? So 2.5 samples. Let's say you have a 100 megahertz scope. So you need 250 megasamples for that channel. And that's just one channel, right? So you need 250 megasamples. So if you have 2 channels, you need 500 megasamples. But if you have 4 channels, then you need 1,000 megasamples, which is, you know, a gigasample, right? So that's why so many scopes have 1 gigasample per second, because they might have 3 or 4 scopes in a series, be 100 meg, 70 meg, and a 50 meg. And so the 50 meg gets extra samples. Does that really help? Well, if you read the Keysight paper and other papers I've read, not really, maybe a little bit. So that's called oversampling. You get more samples than what you really need. And it helps a little bit, but it's negligible, okay? And so one of the things that they go into some math and they kind of show you is a square wave is really a whole bunch of sine waves, right? So a whole bunch of harmonics of the square wave frequency. And so if you add those all together, I did a video on this a long time ago, so I'll see if I can find that and put a link down below. But you add all these sine waves together, and there's a formula showing the amplitude of each of these frequencies, and it starts to turn into a square wave. You know, so if you imagine a bunch of sine waves crossing 0 at the same point, one's a higher frequency, it's going to look straighter, right? And so, you know, the real high frequency ones are going to look like this, straight up and down, compared to like this low wave. So if you add some high frequencies, you can get those waves up, and then the top of the square wave would have this kind of a lobe, and then another lobe, and another lobe, and the more you add together, you start getting it squared off, okay? So when you do that 2.5 times thing, it looks like kind of a little bit of a lobe, and then another lobe, and then it comes down, and it looks the it's square enough on top that it's within margins, and they're like, okay, that's pretty darn good. So that's kind of how they come up with that number. And so when you go more samples, you're going to get a little bit better, but it's starting to become more negligible. Especially, what if you're not looking at a square wave? What if you're looking at a sine wave? I mean, you're not going to see the difference. So for 100 megahertz scope, you need 1 gig of samples. Okay, so 200 meg, 2 gig of samples, right? Okay, this guy back here, it's a 500 meg and it has 2.5 gigasamples per second. So when you start looking at those samples per second, the important thing to do is look in the spec and see, is that just with one channel? A lot of times it is, or sometimes it's 2 channels, and then sometimes it's true with all 4. But most marketing guys won't let you get away with that, because they're going to say, no, let's give it for just 1 channel. But certain scopes work in different ways. Sometimes you turn on channel 1 and another channel, and it's going to divide in half right away. Okay, and sometimes some scopes you can turn channel 1, channel 2, and that's a bank, and that's going to have the same sample rate. And then once you turn on channel 3, then it goes half. Or sometimes in a bank, channels 1 and 2, if you turn on both those channels, it drops in half. So you'll want to, if you do have 2 channels, you want maximum sample rate for maximum bandwidth, then you go channel 1, use channel 1, channel 3. And then that way, each bank has its own ADC processor, and it's going to keep your sampling rate. Okay, so you want to look at your scope specs to see how that operates and see how that's divided up. Yeah, so some of them, as soon as you turn on second channel, doesn't matter, it divides. Okay, so now I said bandwidth. So the gigasamples per second, it's kind of like, you can think of it as the digital bandwidth of your scope, and the megahertz is the analog bandwidth of your scope, and they should coincide. They should be the same. They design that way, so they'll give you 2.5 samples per cycle. So 100 meg, they'll give you 1 giga sample. Okay. All right, guys. I have this Tektronix hiding back here. This is a scope I bought years ago. This is really cool because it has 2 channels. They're isolated from each other. It has a multimeter input over here. They're all isolated from each other. So it's great for power supply stuff. This is a 200 meg scope, and it has 1 gigasample per second. Okay, so 200 meg, 2.5 times that is that 500. And then because there's 2 channels, you need 1 gig. So there you go. So this is years ago they did this, and they follow that formula. And if you look at scopes, here's the thing, is sometimes a scope manufacturer will use the ADC for one scope, like say the 100 meg or the 200 meg, but then they'll offer the 50 or 70 meg in that. So you still get all those samples. But sorry, had to change my memory card. All right, so you know what? This Uni-T, this is an example. If I use channel 1, I get the 2.5 gigasamples, okay? But if I use channel 2, I get half of that, which is still fine for that bandwidth, right? Now, if I want 2 channels, I could use 1 and 3 or 1 and 4, because there's a bank and a bank. So if I use 1 channel in this bank, say channel 2 and channel 3, then each bank I can maximize. I can get the 2.5 gig samples. So I can get that little bit more samples if it helps just a little bit. But other than that, oversampling more than that isn't going to help. So if I had 5 gigasamples, and so some of these scopes offer a higher sampling rate, and there's another way to get a high sampling rate that basically in a bank like this, the reason I can get 2.5 gigasamples and then I go 1.2 is because when I'm only using one channel, it does this interweaving thing. It's not the same as the oversample. Here, let me show you what I'm talking about. Okay, back to the board again. So I have a clock cycle. Let's say this is when my ADC picks up a point. So it goes up here. Now, just to make it easy, I just did 2 points instead of 2.5. So within a cycle, I said, okay, here, about a half cycle later, I get another one. And the timing, obviously here, this is wider than this. So, you know, so I don't have this to scale. And it would have to be perfect. You want these guys to be perfectly spaced. That's actually Nyquist, I think it's his second or third rule that says they have to be equally spaced. Okay, so if there's dither, if your clock isn't perfect, then you're going to get some kind of distortion there too. So that's an important parameter in the scope. And the faster you go with the scopes, the more you can imagine, the more important that is. So that's why the big name brands, or like even the Uni-Ts or the Picoscopes, they're like really fast scopes get expensive fast because all these things start to get so important. Okay, so anyway, there's 2 samples. Okay, so then it's going to clock and it's going to capture another one, this part of the waveform here, and you know, through this chain. Okay, but now let me show you what happens when you interweave. So basically, there's 2 ADCs running. Okay, let me show you that. All right, so here's my second clock for my second ADC. Okay, analog to digital converter. So it's got to be 180 degrees out of phase with the first one. What happens, I come up here and I clock a cycle and I take a sample right there. Okay, and then I get another one when I go high here. So I get another one right here. So now these all have to be equally spaced, okay? So with between each other and all that. So they have to be equally spaced to get a good signal. So now I've got twice as many samples, right? That's how, when I only have a bank going, an ADC says, oh, I'll help you out. I'm just sitting here waiting for somebody to use channel 2. I'll help out channel 1. So he helps out channel 1. He gets twice frequency. Somebody plugs a probe in channel 2. They turn it on. Then channel 2 says, you know, channel 2's ADC says, hey, can't help you anymore. Got to go work on channel 2. So now he's back to half. Okay. And so channel 1 and channel 2 have 2 ADCs and they're working together. If there's only one of those 2 channels working, same with channel 3 and 4. So that's how you can double your sampling rate. Okay, so some of these scopes, the way they work is once you add any other channel, it's going to half. Okay, doesn't matter because they're all in the same bank. It halves it with 2 channels. It halves it again with a third, and then after that, you know, you got what you got. Okay, so yeah, they keep on halving. So that's not as good as when you have 2 banks that operate independently from each other. So you got to look at the specs to see which one of those scopes you have. If you have a really fast sampling rate, you might have one of those that divides down 3 times or even 4 times. Every time you add a channel, it divides again. So yeah, check that out. Okay, so that's one of those tricks they can use. You know, maybe you say, well, it's not a trick because if I only have one channel and I want all these samples, but that's essentially oversampling. You're getting a lot more samples than you need for the bandwidth of the scope. So you're getting negligible improvements once you get over that 2.5. Okay, so, and especially once, you know, certainly once you get over 4 times, then you're really getting super negligible. So up to 4 times. So maybe, you know, when you get 4 samples, then, you know, that's might be something that's useful. But after that, you could argue that it's not really useful. So yeah, be careful when they're just, you know, when they're in that sampling rate race and they're comparing that one spec and they just keep you know, if you see somebody just going, you know, repeating that same spec over and over, because do they ask yourself, do they ever bring up the deep memory? How much memory does it have? How does that work? Because when you're sampling, you got this scope picture, right? And you got, let's say, 10 grids. You're taking all these samples all the way across the grid, and you put up a waveform and you're rebuilding those waveforms, okay? But all those samples have to go into memory. Well, if you're 5 nanoseconds per division, you don't have very many memory slots you have to worry about. But what if you're at 10 milliseconds or 100 milliseconds? Now you've got, if you're taking all those samples, you know, gigabits of samples for that long, that's a lot of memory. So what you'll see is scopes that as you get more time base, like you start doing, you know, 5, 10, 20 mils, 100 milliseconds per division, you'll see the max sampling rate drops because it doesn't have the memory to store. It can't store all those samples, so it doesn't know what to do. So that's where, you know, like they haven't brought up all the parameters of the scope together. They focused on one to give you like this, you know, false idea that you got this super fast, super cool scope. You got a drag racer, but you don't have a lap car. I mean, so if you want to do all those things well, you want to ask, well, what's the deep memory? You know, how much deep memory it has. That's super important. So the samples and the deep memory work together. You can see because you have to store those in memory as you're sampling. And so, yeah, I just want to bring that up. You know, the sampling is a way of saying digital bandwidth, and then the megahertz is the analog bandwidth, and they have to kind of go together. And if they don't, you know, you can't have a super wide megahertz bandwidth if you don't have the samples. And you can't have, I mean, if you have way too many samples than you need, then yeah, it's just bragging rights, but it's not really useful. And if you don't have the memory with all those samples, you can't, then you're fixed to really small time bases, like, you know, 10 nanoseconds per division. And like, how many of us ever put our scopes in those real fast things? So even if you're doing memory, like you're looking at really fast moving edges, and you're like, yeah, but I need it for that. Well, but you're also going to want the memory so that you're not limited in your time base, like how many seconds, nanoseconds, microseconds you can get. You want to be able to see multiple waveforms so you can see a broader picture and then zoom in on the ones where you see an issue. Otherwise, all you're going to do is catch a rising edge in half a waveform, or just the edge of the waveform, and you're not going to be able to capture any more of it because you don't have enough memory to get those samples in a longer time base. So does that make sense? I was hoping to clear that up, because when I talk about this, I'm going to show you waveforms in that, and maybe that'll make more sense. But besides those things we're talking about, you know, the bandwidth of the scope and the memory, which are all interlinked, without, you know, and I've been talking about vertical bandwidth. You know, 8-bit scopes have been around for a long time. I've been saying, hey, we should be going 10-bit at least, 12-bit scopes. And so finally they did. And so now there's a number of them out there. Some of them are really low cost, but it's that one parameter they're focusing on, and some of those other things they don't have. So that's why these scopes that cost, say, a few $1,000s or over $2,000, that's why these scopes are worth that, because there's all those things they've brought up to the same levels. Not only that, that trigger that I'm talking about, I'm going to show you the triggers. The triggers are so good now. It's crazy good how they are. And the other thing is, if you do CAN bus or, you know, other types of buses, you know, if you're doing I2C, you know, there's a whole bunch of them, SPI bus, you know, there's a bunch of them out there, UARTs and that. Well, when you're doing that kind of stuff, can you decode them? And when you decode them, are you fixed in just one little simple decoded bucket, you know, that gives you a hex number or something, or will it do more for you? And so there's things like that with, and also like how many buses are there? There's an airing that's really unusual, and that I remember one scope manufacturer wanted to sell that, just that one thing, for quite a bit of money, like a few $100. Which brings up another thing. A lot of these scopes, when you buy them, the add-ons, like the little pod that goes in here, there's a little digital pod for 16 channels. Well, a lot of those pods, I want to say they're minimum $250, $350 average for those pods from the different scope manufacturers. I mean, we're talking the lower cost guys. If you're talking Tektronix, Keysight, and that, they're quite a bit more, right? All that stuff comes with a scope like this. So, but the add-ons, you have to worry about the add-ons. And there's generators built into the scopes now. Like there's 2 generators on this one. There's 2 generators on this one. So what can you do with those generators? How good's the FFT? How's that changed? So there's all these other things that are so important to make a scope just a universal tool to do all these things you want it to do. And if you are in need of those really fast, you know, sample rates, wide bandwidth scopes, you're going to be spending some money. For instance, a Tektronix scope that has, say, a 12-bit that compares to, say, that guy there, I think I want to say they're $11,000. Okay, they're over $10,000. And this guy's like a third of that, roughly. So, you know, when you start getting the higher speeds, you have to have somebody that really knows signal integrity and scopes. So, point of this video is just kind of give you an idea of how that sampling works and how the math works and how important is it. Don't get in the the megapixel race like the camera people did. I mean, somebody's bragging about how many samples. This is 5 gigasamples. This is a 1 gigahertz scope at 5 gigasamples or something like that. You know, if they're bragging about stuff like that, it's like, that's probably, if it's a low cost scope, it's probably 1 channel, and you're probably limited on what time bases you can use. There's probably you probably have to have all these things lined up to get those numbers, like you're getting ready for a drag race. So versus universal tool that has a whole bunch of parameters that you're going to be excited to use and that are very useful, and it makes it easier to use. And also just the idea that when you do bring up one thing without bringing up the other things, then you got to ask yourself, how useful is that? So all right, guys, so I wanted to explain that, because when we get into talking about these higher end scopes and you're fixated on, yeah, but the sampling rate of this isn't as good as that scope that's, half or third the price. It's like, yeah, but can it do all these other things? And so, all right, guys, hope you like that. Hope it was useful. Give me your comments below and let me know what you think about that. And yeah, the sampling, super important stuff. The interweaved sample thing, that's kind of an interesting concept they came up with. And the ability to lock those clocks 180 degrees and to make sure they're not dithering, like they're like just a little bit. That, let's say it's 50% duty cycle, everyone's exactly 50% duty cycle, right? And the clock is just nailed down. Nothing's ever perfect, so there's always going to be little bits of distortion from that stuff. When you start going, like, I'd say above 500 megahertz, things start getting really squirrely fast. So yeah, think the super fat, like 5 gigasamples, those numbers and above are starting to get crazy fast. Once you get above 1 or 2 gigasamples, those are just crazy fast numbers. And so they've been doing 1 gigasamples for a long time. People have figured out that stuff. Now with the ASICs and all that stuff that they're using, a lot of that stuff, it's not a whole bunch of chips on a board. It's one chip doing a lot of that stuff. But we're going to take a look at this scope in the next video on, I think I got another video before I do that. But hope you like this, guys. Sorry, probably went long. So guys, I want to say 2 big thumbs up to my patrons and my YouTube members that support the channel. I really appreciate you guys. Danny for being a team member. Thanks for supporting the channel. And yeah, if you want to hit the super thanks button down below, just hit the thumbs up. That supports the channel a lot. Share, subscribe, do all those things. All right. Thanks, guys. See you next time.